Good morning to all of you. We will continue with our discussion in magnetostatics. You may remember the last lecture we had introduced Biot-Savart law, and from Biot-Savart law we calculated the magnetic field produced by a current loop and also the magnetic field produced by a infinitely long straight current carrying conductor. So, let me recall. So, if you have a infinitely long straight current carrying conductor with current I passing through the wire, then we calculated the magnetic field at some point P at a distance x from here. So, we call this as the x axis and this is the y axis here, and we calculated and showed that the magnetic field B is mu naught I by 2 pi x minus sin k k, and the magnetic field at this point is pointing inside the paper. So, magnetic field is going into the paper here, and we had calculated by using Biot-Savart law by taking a small current element here, then using that current element to calculate the magnetic field at this point and integrating over all current elements. It is interesting to note that all current elements produce magnetic fields in the same direction. So, all we had to do was to add the magnetic fields due to each element and get the total magnetic field. Now, we also note that because of symmetry, the magnetic field will be the same at all points which are at the distance x from here. So, we can actually generalize this and write that if I have a current carrying conductor like this, and if I calculate the magnetic field at any point which lies on a circle of radius r with the wire at the center, then B magnitude of B will be mu naught I by 2 pi r, and the direction of the magnetic field will be according to the right hand rule. Please note that if the current is going upwards with the right handed screw, if I move the screw in this direction, then the screw will move up. So, if the current is going upwards, the magnetic field has to curl around the wire like this in this direction. So, this is the magnetic field magnitude independent of distance, independent of z axis along this length of the wire, independent of angle, and it only depends on the distance of that point from the wire. And also note that magnetic field lines form closed lines. So, if I were to draw the magnetic field from the if this is the current carrying conductor carrying current towards me, the magnetic field lines will look like this, or closed loops around the current carrying conductor, and again the direction of the magnetic field is determined by the direction of the current that is flowing through this. Because of the right hand screw rule, the current magnetic fields are in the anticlockwise direction when the current is coming towards me. So, this also implies that if you take any closed surface, suppose I take a closed surface S, as many field lines will enter the surface as will go out, and you have this equation, the Gauss's law for magnetic fields, integral B dot dA is equal to 0, which essentially implies that there are no sources of magnetic field lines, that magnetic field lines do not start from any point and end at any other point. They form closed loops, or they start from here and go to end at infinity. So, this is contrary to the equation satisfied by electrostatic fields, where the flux was equal to the charge net charge enclosed divided by epsilon 0. From this calculation of the field produced by a current carrying conductor, we had derived an equation which is the Ampere's law. So, let me recall again. So, we had, if this is the current carrying conductor, and if I take a circular loop around this point and integrate B dot dl around this loop, I showed you last time that this is equal to mu naught times I. That is the integral over the loop from across the in the circular arc here is equal to B dot dl, integral B dot dl is equal to mu naught I, that is called Ampere's law. Now, this law is always valid. It is very similar to Gauss's law in electrostatics. It is always valid. It is very useful, as I will show you, whenever you can take the magnetic field be outside the integral, then you can actually use this integral formulation to calculate the magnetic field, otherwise it is always valid. So, what we did essentially was to integrate over this circular path. So, let me recall. So, what we did was we took I taken small element here dl length here. So, if this is angle is d phi and this distance is r, then dl vector magnitude is equal to r d phi, and the magnetic field is also along the same direction as dl vector. So, b dot dl is equal to b times dl, which is equal to b times r d phi, and magnetic field I just calculated mu naught I by 2 pi r into r d phi, which is equal to mu naught I by 2 pi into d phi. So, if I integrate, integral b dot dl becomes equal to mu naught I by 2 pi integral d phi. Integral d phi is the complete angle surrounding this point, which is equal to 2 pi. So, this gives me mu naught I. That is what we had used to calculate this equation value for integral b dot dl, and that happens to be mu naught I. Now, this is a calculation assuming that the wire is at the center of this circular path. Now, I want to show you that this value of the integral is always mu naught I irrespective of the path that I take around the current carrying conductor. So, let me again draw a figure here. So, this is my current coming out of the plane of the paper. So, I take some arbitrary path like this around this current carrying conductor. So, let me try to draw a figure here. So, for example, at this point B vector is perpendicular to this line, this is the line joining the center to this point, B vector is like this and dl vector is here. So, let me call this angle in between as theta. So, let me draw another line here. So, what is B dot dl? B dot dl is equal to B dl cos theta. Theta is the angle subtended between B vector and dl vector. So, dl vector is along the path which is not necessarily circular with the wire at the center. So, dl dot b dot dl is b dl cos theta and dl cos theta is this length. So, dl cos theta is this length, and if I call this angle d phi and this distance r, dl cos theta happens to be equal to r d phi. R d phi is this distance times the angle d phi, and that is also dl cos theta. So, b dot dl becomes nothing but b r d phi. So, for this case b I know is mu naught I by 2 pi r into r d phi. So, that gives me mu naught I by 2 pi into d phi. So, integral b dot dl would be equal to mu naught I by 2 pi integral d phi, which is again 2 pi because the entire angle covered by phi, which is nothing but mu naught I. So, even if I have a path of integration which is not circular with the wire at the center, what I have shown is that this integral b dot dl is always equal to mu naught times the current in the conductor, which is enclosed by this loop of integration. So, although b and dl are not parallel to each other, b dot dl happens to be b r d phi, and when I integrate I just get mu naught I. Now, what will happen if I, so how did I choose the direction of integration here? The loop of integration is such that it happens to be along the magnetic field, because for a current carrying conductor with current coming up towards me, the magnetic field is anticlockwise. I can also do an integration in the clockwise direction. So, for example, if I have a current carrying conductor like this and if I have a loop like this with integration in the reverse direction, then integral b dot dl will be minus mu naught I. Here this is over curve C2, and the same current carrying conductor, if I have another path with C1 like this, integral b dot dl is equal to mu naught I. So, it depends on the path that you are taking around the current carrying conductor. If it happens to be along the direction of the magnetic field satisfying the right hand rule or the reverse direction, you can have plus mu naught I or minus mu naught I. This also tells you that I can actually, if I have not just one conductor, but suppose I have more than one conductor carrying current. So, let me assume that I have a current carrying conductor with current I 1 and another with I 2, and I form some loop like this. So, integral B dot dl will be equal to integral B 1 plus B 2 dot dl, because magnetic fields satisfy superposition principle. So, the total magnetic field at any point is the sum of the magnetic field because of I 1 and magnetic field because of I 2. So, this is nothing but B 1 dot dl plus integral B 2 dot dl, and this is nothing but mu naught I 1. This is the current, this is equal to mu naught times the current carried by conductor 1 and plus mu naught times I 2. So, this is nothing but mu naught times I 1 plus I 2. So, what I can show by choosing many currents is that integral B dot dl is equal to mu naught times I enclosed here, which I have shown here. Now, what happens to conductors which are carrying current, but which lie outside the path of integration? So, let me take an example here. So, I have a current carrying conductor here and I take a path like this. So, what happens? Now, what I do is, let me draw a line here. So, let me say that this corresponds to angle phi 1, this corresponds to angle phi 2. So, integral B dot dl I need to calculate. Please remember, I had just now shown you that for an arbitrary path dl cos theta is r d phi. So, B dot dl is nothing but B r d phi. So, I will get this is integral B r d phi, which is equal to integral mu naught I by 2 pi r into r d phi, which is equal to mu naught I by 2 pi integral d phi, r cancels off, which is so this is equal to mu naught I by 2 pi integral phi 1 to phi 2 d phi plus. So, I go from phi 1 to phi 2 along say C 1, and then I come back. So, I go from here to here along this curve and I come back along this. So, phi 2 to phi 1 d phi, which is nothing but mu naught I by 2 pi phi 2 minus phi 1 plus phi 1 minus phi 2, which is equal to 0. So, integral B dot dl along this closed path, which does not enclose the current carrying conductor, happens to be 0. So, any current element lying outside the loop of integration does not contribute to integral B dot dl, and that is why I can actually write. So, if I have multiple current carrying conductors, so I can write integral B dot dl is equal to mu naught I enclosed. That is Ampere's law. Now, couple of things I must mention. I have been drawing curves which lie in a plane. The curve of integration, the path of integration may not lie in a plane. So, I can have a wire carrying current like this. So, I can integrate some arbitrary path like this, and I will still get mu naught times the current enclosed. Of course, whether it is plus mu naught I or minus mu naught I depends on whether I integrate the direction of integration, whether it corresponds to the right hand rule with respect to current carrying conductor or not. So, I can have an arbitrary path, some arbitrary path which may not lie in a plane, but in the figures that I am drawing here the curves seem to be lying on a plane. So, this is a very general result. So, I could, for example, I can draw a figure in which I can say that I can have current carrying conductors like this I 1, another current carrying conductor I 2, and another one for example I 3. So, I can have a loop of integration which may be going behind, coming like this. So, although this currents are not, the curve is not in the plane containing the current, I still have this integral B dot dl is equal to, now in this case as you can see here, this direction corresponds to positive direction with respect to this current. So, this is mu naught I 1 minus I 2 minus I 3. So, and if I have another current carrying conductor here for example I 4 does not contribute to this integral, or because it is lying outside the loop of integration. Just like I had mentioned in electrostatics, I must mention here that the magnetic field at every point is determined by all current carrying conductors. Just like in the electrostatics case in Gauss's law, the electric field is determined by electric field produced by all charges, while the flux over a closed surface depends only on charges inside. Similarly, the magnetic field produced at any point, for example in this figure, magnetic field produced here is because of current I 1, I 2 and I 3 and I 4, but when I integrate B dot dl, the only currents that contribute to the integral value are the 3 currents enclosed by this loop. So, please do not forget that magnetic fields at any point are generated by all currents. In Ampere's law, in integral B dot dl, only the currents which are contained within the loop contribute to this integral value. So, integral B dot dl, suppose I find in a situation integral B dot dl is equal to 0, this does not imply magnetic field is 0. As you just now saw, if the loop of integration exists outside the current carrying conductor, B dot dl is 0, although the magnetic field at every point was not 0. Now, I want to leave a problem here for you to think. So, let me look at it from above. So, I have a current coming towards me 5 amperes, I have another current here going inwards 5 amperes and another current which is coming towards me 10 amperes. So, let me consider 2 loops, one this one and one this one. So, find the values of integral B dot dl for paths C1 and C2. Draw paths for which integral B dot dl is maximum and positive and maximum and negative. And finally, draw another path having the same value of integral B dot dl as over C1. So, you calculate integral B dot dl for C1 and C2, draw paths for which integral B dot dl is maximum and positive and maximum and negative, and then you have already calculated for path C1, draw another figure, another curve for which integral value of B dot dl is the same as for C1. So, just give some thoughts to this problem and it will help you to understand better the application of Ampere's law. Okay, so, I want to apply Ampere's law for certain situations, and just like we did for Gauss's law we obtained Gauss's law and applied Gauss's law to calculate electrostatic fields over charge distributions. Now, remember what we found is Gauss's law is always valid. It is useful in certain situations where there is symmetry, because in symmetric situations I can take the electric field out of the integral in Gauss's law, and that will help me to calculate the electric field distribution. Similarly, here Ampere's law is always valid. Ampere's law is useful whenever I can take the magnetic field outside the integral by some symmetry arguments and use that to calculate the magnetic field. So, we will start looking at some examples. The first example I want to look at is an infinitely long and straight current carrying conductor. So, this is my current carrying conductor. Now, first thing I notice is because of symmetry, magnetic field cannot depend on z, this distance. It has to be the same here, 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 everywhere. It is an infinitely long wire. It cannot depend on this angle, because if you have a current carrying conductor, this point is the same as this point. I mean, it has to be the same. It cannot have an angular dependence. The only dependence it can have is a r dependence, that is the distance from here. And the magnetic field, although magnetic field has an r dependence, it has 3 components. It can have 3 components. It can have this component, it can have this component, and it can have the perpendicular component. A component parallel to the wire, a component perpendicular to the wire, and a component parallel to the wire in the other direction. Now, I can, for example, think in terms of Biot-Savart law and see that if I have every current element along the wire will produce a magnetic field which is along this direction. No element in this current carrying conductor will ever produce any magnetic field along this direction or along this direction, because please remember the magnetic field direction is, so this is dl vector and this is r vector. So, dl cross r is the magnetic field direction, that is always perpendicular dl and r vector. So, it lies like this. So, the magnetic field has to be azimuthal. So, if I look from the top, this is my current carrying conductor, the magnetic field can have only this component, a component perpendicular. So, if I have a magnetic field here, can be only like this, here it will be like this. Now, I can also use some symmetry arguments to show that magnetic field cannot have this component and this component, but here I am just using the Biot-Savart law to convince you that the magnetic field, whatever exists, has to be in this direction. Now, once I know the direction of the magnetic field and once I know that the magnetic field does not depend on this angle, I am going to use this equation. So, this is my Ampere's law. So, what I do is I take a circular path around this wire with the wire at the center with a distance r. So, remember at every point dl is like this and b is also like this. So, at any point b is parallel to dl vector, and so b dot dl is nothing but b dl. At this point b is like this, dl is like this, at this point b is like this, dl is like this. So, I am, please remember, for this integration I can choose any path, just like Gaussian surface I can choose any Gaussian surface, I can choose any curve which I want in this integration. So, my choice is a circular path around the wire with the wire at the center, so that it will help me to integrate the left hand side. And what is dl? So, dl, for example, if this angle is d phi and this is r, dl is nothing but r d phi. So, b dot dl is b r d phi, and so Ampere's law gives me integral b dot dl is equal to mu 0 times the current enclosed, which is just the current I carried by the conductors, which is mu naught I. So, this is nothing but integral b r d phi is equal to mu naught I. Now, B is independent of phi. B is the same here, 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 everywhere is the B is the same, because I am taking a circular path with this wire at the center. So, B here, everywhere is the same. So, I can take B out of the integral, and of course, r does not depend on phi. So, B r integral d phi mu naught I, which is nothing but B r integral d phi is the total angle subtended by the circle at this point, which is 2 pi. So, 2 pi is equal to mu naught I. So, magnetic field I have got is mu naught I. The same as before. So, Ampere's law, although please remember I have obtained Ampere's law by deriving the magnetic field due to a infinitely long current carrying conductor. The Ampere's law is a very general law, it is valid for all situations, and I am again using the Ampere's law to calculate the field due to a current carrying conductor, infinitely long current carrying conductor. And in the infinitely long current carrying conductor, I can use some symmetry arguments to find out the direction orientation of B vector and the dependence of B vector on the distance from the wire, the position along the wire, the angle with respect to wire, etc. All this I can, through symmetry arguments I can find out, and then I choose an appropriate path of integration which will help me to take B out of the integral. This is what I have done. So, I have taken a circular path around the wire. If I take some arbitrary path, I will not be able to do this. So, I must choose an appropriate path, a judiciously chosen path of integration. And here my judiciously chosen path is a circular path around the wire. And because I have chosen that path, B happens to be parallel to dl at every point. So, I can write B dot dl as B r d phi, and B happens to be independent of phi. So, I can take B out of the integral. I could not have done this if B was a function of phi. So, I am able to take B out of the integral and immediately integrate and get the magnetic field. So, that is a very interesting example which tells me that the magnetic field of a infinitely long current carrying conductor is nothing but B is equal to mu naught I by 2 pi r, which we had obtained before by using Biot-Savart law. Now, I want to take another example. Current distributed uniformly over the cross section of a cylindrical wire of circular cross section and infinitely long. So, it is something like this. I have a thick current carrying conductor, and current is flowing like this in the carrying conductor. So, let me assume the radius is r. So, the top view will be looking like this. I have a circular wire. So, current is flowing towards me at every point, equally distributed, and so I have to find the magnetic field of this both inside the wire as well as outside the wire. Now, I can use the same argument as for a infinitely long thin current carrying conductor and say that the magnetic field cannot have a dependence on this position, because infinitely long. So, this point, this point, this point, all these points are exactly equivalent. So, magnetic field cannot have a dependence on this coordinate, because it is a cylindrical cross section of a circular cross section wire. Magnetic field cannot have a phi dependence, dependence on angle. That means, it will be the same everywhere as a function of angle. If I take certain distance and calculate the magnetic field at any point along the circle, it has to be the same, because there is no difference between this point, and this point. So, it has to have, it cannot have a phi dependence. So, magnetic field can only have an r dependence. The radius, the distance from the center of the wire, it can only depend on r. Now, Again what I find is, because these are, I can consider these to be a large number of thin current elements going along this direction, they will all produce a magnetic field which is azimuthal and which is along this direction, and I can use this immediately to calculate the magnetic field of the current carrying conductor. So, this Ampere's law tells me B dot dl is equal to mu 0 I enclosed. So, if this is my current carrying conductor of radius r, I take a path inside of radius r. Now, one can show through similar arguments, symmetry arguments, that the magnetic field has to be along the direction, this azimuthal direction, which is the direction which is tangential to a circular path around the center. So, if I take a path, this path, integral B dot dl is equal to mu 0 times I enclosed. Now, I am having a total current I passing through an area pi r square. The total area of the wire is pi r square, and the current is distributed uniformly across the wire. So, the current I is carried over a wire of cross sectional area pi r square. So, I can define what is called as the current density, which is current per unit area, which is I by pi r square. So, if you take a unit area perpendicular to the wire, I will find a current which is passing is I by pi r square. So, the current enclosed by the path C1 is equal to current density into area of C1. Which is nothing but I by pi r square into pi r square. I by pi r square is current density multiplied by the area of this enclosed by the circular path here, this area, and I get this. So, the current enclosed is I into r square by r square. Okay, so, the current enclosed is I times small r square by capital R square. Now, as I told you, the symmetry arguments tell me that the magnetic field is in this direction along the circular arc. So, B dot dl will nothing but be integral B dot dl will again be equal to integral B r d phi, and because B is independent of the angle, the same at every point at different angles, this is nothing but B times r times integral d phi, which is nothing but B times r times 2 pi. So, I get using Ampere's law B times r times 2 pi, which is equal to mu naught times I enclosed, which is equal to mu naught I r square by capital R square. So, this tells me B is equal to mu naught I r square by r square into 1 by 2 pi r, which is nothing but mu naught I into r by 2 pi r square. So, magnetic field is now proportional to small r. It has a dependence like mu naught I r by 2 pi r square. So, the magnetic field at r is equal to 0, the magnetic field is 0, the magnetic field increases as you go away from the center, and this is only valid, this formula is valid for a path lying inside the conductor. So, that is small the path C1. So, that is for r less than r, because our path is inside the conductor. Now, what happens to a path outside the conductor? That is r greater than r. So, that is my conductor R, and I could take a circular path outside. So, the current is coming towards me. Now, the same arguments tell me that the magnetic field has to be along the direction of this circular path, because the circular path has this point at the center. So, the magnetic field is along the circular path. That again tells me integral B dot dl is equal to integral B r d phi, which is equal to B times r times integral d phi, which is equal to 2 pi B times r. And what is current enclosed is nothing but I, the total current carried by the conductor. So, I get 2 pi B r is equal to mu naught I, or B is equal to mu naught I by 2 pi r. And this is the same as the magnetic field produced by a current carrying conductor of carrying current I. So, it does not depend on the size of the conductor. Outside the conductor, the magnetic field is as if the entire current was passing through the center of the current carrying conductor. So, I have got the two expressions here. So, let me write it down. So, B is equal to mu naught I by 2 pi r square r for r less than r is equal to mu naught I by 2 pi r for r greater than r. Notice that B at r is equal to, from this equation, mu naught I by 2 pi r, and it is the same as from this equation. So, B at r is the same. So, magnetic field is continuous across the boundary. So, if I draw a figure here, so this is my current carrying conductor. So, this is R. So, look at this formula. Magnetic field at r is equal to 0 is 0. So, this is magnetic field here. It increases linearly with r. So, it goes like this up to the point capital R, and then it decreases 1 by r. So, from 0 to r, the magnetic field increases linearly. This is some constant here outside, and then it decreases as 1 by r outside the wire, and so that is the distribution of magnetic field for a current carrying conductor of radius r. And the direction of magnetic field can be obtained by simply looking at the right hand screw rule and finding out the direction. And in this case, the direction is, if the current is coming towards me, the direction of the magnetic field is anticlockwise. Now, we would like to look at another example. Coaxial conductor. So, the problem is the following. So, I have a one conductor here and another one which is outside. So, this current flowing like this in this conductor and current flowing backwards in this conductor outside. So, the cross section will look something like this. So, current is coming towards me, for example, here, and current is flowing away from me here. It's uniformly distributed across the cylinder here. Same current. So, a current I flows in from here and flows back from here. It is coaxial conductor because there are two conductors, one lying coaxially within inside. This is on the axis of the outer cylindrical conductor. So, what is the magnetic field? Now, please note that again, because of symmetry, magnetic field cannot have a dependence on this position along the conductor. It cannot have a dependence on the angle. So, it has to be the same at all points along this angle. It can only have an r dependence, where r is the distance from here. It only have an r dependence, and my objective is to find the magnetic field between the points, the radius a and b. Now, so what I do is I take a path of integration. So, this is my inner conductor, that is the outer conductor here. The current is coming towards me here. So, here is away from me, and in the central conductor it is towards me. So, I take a circular path here. Now, As you can see here, this current is not enclosed by this path. So, integral B dot dl is nothing but mu naught I, the current carried by the inner conductor or the current carried by the outer conductor, but it only has one I. And again, because of symmetry, you can show that this is 2 pi r into B, and magnetic field happens to be mu naught I by 2 pi r. This is for r greater than A, less than B. So, this radius is A, this radius is B. Now, I leave it to you to find out what is the magnetic field outside. So, at this point, for example, outside the coaxial conductor, what is the magnetic field? So, I leave it to you. Please try to use Ampere's law and to find out what is the magnetic field outside the coaxial conductor pair. It is an interesting problem, and you will appreciate this because coaxial conductors are used in many electronics experiments, and these are very important components of electrical engineering and electronic instrumentation. Now, I want to look at another device which is a very, very important device. Another example, solenoid. So, solenoid is a device which has usually a circular cross section, and it has current carrying wire wound around it. So, let me draw a, this is like a coil. These are usually very closely wound coils, and I can have a current either flowing upwards or downwards. For example, I can have a current which is flowing downward here in all this. So, there is the wire which comes from here, it goes around and finally comes out from here. So, this current carrying currents are equal current is passing through all the wires. So, I take a long wire and wrap it around a cylinder, very closely wound wires, tightly wound, and this is called a solenoid. And this is used to create magnetic fields, strong magnetic fields, and usually we define the number of turns per unit length which means I take a small length unit length of this and calculate the number of turns. So, that is a quantity which I would know, which I would need to know, because that will define, as we will see, the magnetic field. So, if it is closely wound, it is as if each was a circular loop. Actually, the circular loops are going like this, like helix, but if they are very, very closely wound, I can assume that each winding is a closed loop like this, and these loops are all carrying currents, and all of the loops are carrying the same current. So, my problem is to find out what is the magnetic field produced by this, and I would like to take an infinitely long solenoid. Infinitely long essentially implies that if the radius is A and the length is L, L is much greater than A. So, my length of the solenoid is very large compared to the dimension of the solenoid. So, if I have a solenoid, I will be looking somewhere near the center. So, for effectively the end effects just disappear. Remember, in a capacitor we had the same problem. We had a capacitor with a finite size plates, and we assumed that the plates are of infinite extent. Otherwise, I have to look at some end effects, and here, so I do not bother myself with end effects. I have an infinitely long solenoid, and I want to find the magnetic field within the solenoid. So, I want to use Ampere's law. So, to use this law, I must find out what will B depend on, what coordinates, and what will be the direction of B. So, let me draw the solenoid here. So, this is my solenoid. Now, first I take a surface like this. Now, first thing to notice is that, again, because of its infinitely long, the magnetic field cannot have a dependence on this coordinate. It has to be the same every point along this, and because it is azimuthally symmetric, I am assuming that it is very closely wound coil, it cannot have a phi dependence. If at all, it can only have a dependence on r. If at all, it cannot have a dependence on z, it cannot have a dependence on phi. So, let me take a surface like this. So, this is the top surface. So, this the surface is cutting through this is the closed surface, and I know magnetic field satisfies this equation. The Gauss's law for magnetic fields is B dot dA equal to 0. Okay, now, so this is my lower surface here and the upper surface is here. So, let me call this S1, this S2. Now, please note that because the normal to this surface is like this and the normal to this surface is like this, the dA vector on this surface is pointing up, the dA vector on this surface is pointing down. Remember, recall Gauss's law, when you do an integration like this, the dA vector is an area vector with the outward normal. So, dA vector here is upwards, dA vector here is downwards. Magnetic field is independent of this distance. So, you can immediately understand that the flux that is exiting from the upper surface must be exactly equal to the flux that is entering from the lower surface, because remember the normals are oppositely oriented. So, if the magnetic field happens to be pointing upwards, then as much flux is entering here as is getting out here, because magnetic field here and here are the same, areas are the same. So, they have to cancel each other. So, the integral area over S1 and S2 just cancel off, whether the magnetic field is pointing downward or upward or any angle, because there is no dependence on this position, as much flux is entering or leaving the lower surface as much as leaving or entering the upper surface. So, the only integral which will be left will be over S3, and because there is no dependence of magnetic field along this direction. So, if I call, for example, suppose let me look at the top surface here. So, this is my solenoid and I am taking this a path like this. This is my part of the surface. So, this is the r cap direction. The normal here is like this. So, what I will get is B dot dl. So, dl, so dA. So, dA vector is also in the same direction. So, this will be B dot Br into dA. So, Br is this component, dA is the same component. So, at this point dA is like this and Br is this direction. So, at this point dA is here and Br is the direction, and Br is independent of this. So, what I will get is Br integral dA over surface S3 will be equal to 0, that is Br into 2 pi r at this length L. This implies Br is equal to 0. There can be no radial component of the magnetic field. Magnetic field cannot have a component pointing away from the solenoid. So, I have used Gauss's law for magnetic fields to show that magnetic field cannot have a radial component for the solenoid. It is closely wound infinitely long solenoid. Please remember, I am calculating the magnetic field for an infinitely long closely wound, very closely wound solenoid. Now, let me take another integration. So, this is my solenoid and I take a circular path like this, and I want to use this equation, Ampere's law. So, from the tops, if I look from the top, that is my solenoid and I am taking a path, circular path like this now. That is a solenoid, okay, that is a solenoid, and my path is like this and this is r. Now, so because my path is like this, if I call this as a component B phi, this is d phi. B phi is the phi component of the magnetic field, which is the azimuthal component. which is along the tangent to the circle. Now, please note that in my solenoid I am assuming very tightly wound solenoid. So, the coil is like this, so my curve goes like this, and if you look at this curve, there is no current entering or leaving this path, because the current is lying inside here and the other currents are not at all crossing the path. There is net current which is entering or leaving this path, circular path, which is perpendicular to solenoid. Solenoid is like this now and my path is like this. So, the right hand side current enclosed will be 0, and because the integration is along this curve, I will get b phi into 2 pi r must be equal to 0. 2 pi r is the circumference of the circle. So, b dot dl becomes b phi into r d phi, and I get b phi dr. This implies there can be no azimuthal component, there can be no component which is so if the solenoid is like this, first thing I showed you is there can be no component of magnetic field like this. I have also shown you there can be no magnetic field component in this direction. There can be no magnetic field component like this. In fact, this you can actually use Biot-Savart law with current elements in different directions to find out again using symmetries to tell you finally that magnetic field has to have only component Bz component. So, z axis is like this now. So, for the solenoid, it cannot have a component like this, it cannot have a component like this. Sorry, yeah. So, it cannot have a component like this, which I showed you first. Here I showed you that it cannot, suppose this is my solenoid is like this. So, it cannot have an R component, it cannot have a component away from this solenoid, it cannot have a component along the azimuthal direction. The only component left is the z component. So, that is the only component which can survive. Now, once having obtained this, now I can use Ampere's law to find out the magnetic field of a solenoid. So, let me draw the solenoid again here. So, this is a section of the solenoid. So, the current is coming towards me and this is entering here. These are the coils. Now, first thing I do is take a loop outside. So, please remember so z axis. B can only have a z component and it can only depend on the radius r. So, now I use this Ampere's law here for this loop integral. So, this is the curve C. Now, this loop does not enclose any current. So, this must be equal to 0. So, integral a to b b dot dl plus integral b to c b dot dl plus integral c to d b dot dl plus integral d to a Now, because magnetic field has only a z component, B c this integral must be 0 and this integral must be 0, because remember the path of integration is like this and the magnetic field can only have a z component. So, these two integrals are 0 and magnetic field does not depend on the position at all. So, if I call this R1 and this is R2, B at R1 first integral is times if this length is L plus B at R2. Now, please note the direction of integration is opposite. So, minus B at R2 into L must be equal to 0, and this implies B at R1 must be equal to B at R2. So, magnetic field seems to be independent of the distance from the axis. So, that is another result we have got. So, what I will do is I will stop my lecture here. In the next class I will continue with this discussion, and we will then calculate with all these arguments what is the magnetic field inside the solenoid and outside the solenoid. And before I leave, let me see here that I know that the magnetic field at infinite distances from the solenoid must be becoming 0. So, if I tend R2 to infinity, it must be becoming 0. So, B outside the solenoid is 0. So, B outside the solenoid so that is something we have obtained today. In the next class I will calculate, I will take another Amperian loop and I will calculate and show you that the magnetic field within the solenoid is uniform, and we will calculate the magnitude of the magnetic field.